All right, I'm going to do a one-way repeated measures ANOVA for you guys here. Something to note, I've got the slides open from the lecture for chapter 13. I've got an F table in here. I've got a Q table. So these are the things we're going to need. I'm going to be doing everything in an Excel sheet, but you should still be able to follow along and see, what it is that I'm typing in here to get the answers, right? To finish off sort of computing the statistic. Okay, so let's look at a little problem I've devised. All right, so a beer maker wants to test the bitterness level of hops at their farm over a 3-year period. They randomly select 5 hop plants and measure the bitterness rating for each plant in years 1, 2, and 3. The bitterness ratings are recorded below. Use the following steps to conduct a one-factor repeated and measures ANOVA to test whether there are any differences in bitterness between the 3 years. So here's the data, right? So plant 1 in 2016 had a bitterness rating of 9, 2017 had a bitterness rating of 4, and 2018 had a bitterness rating of 5. So these are the 3 values that this particular plant, this one plant, produced over the 3-year window, right? So we've got one sample here of 5 plants. Here's their data for 2016, 2017, 2018. So I'm going to do this from scratch, right? I'm going to do all the steps, but you'll note when you get to the homework that there's a few things I've already done for you, right? Like I've already computed the individual sums of squares. I think I've already done the sums for P and T and all that other stuff. There's some stuff you're going to need to do, but I've given you quite a big head start on the homework, but that doesn't matter because I still, it's important that you sort of, understand how to do this. So let's start off by stating the hypotheses. So we're going to say the null, right? And I'm not going to mess with getting all the little graphics on here. What I'm just going to say is mu1. And remember, though, when you write this out on your homework, make sure you're using the Greek letter for mu, right? But for our little example, hopefully this is clear. So mu1 equals mu2 equals mu3. And that's it, right? And what we're saying here is the null hypothesis is there should be no difference between the 3 means. Whereas our alternative hypothesis should be not the null, right? And that's all there is to it, right? We've talked about this before. We talked about this yesterday, or in lecture, rather. Depends on where you're watching this. But it's the same thing. So stating the hypotheses for repeated measures ANOVA is exactly the same way you would state the hypotheses for a between subjects ANOVA. So that's easy enough. Next, we've got to determine the critical value for an alpha level of 0.05. And be careful here because the homework, I think, for the problem that this example relates to, if I recall correctly, is asking for a critical value of 0.01. So, like I always say, make sure you read the problem carefully. All right, so we're going to need 2 pieces of information here in order to look for our critical value in the table. We're going to need degrees of freedom for our numerator, which is our degrees of freedom between groups. And then we're going to need a degrees of freedom for our denominator. Now remember, since this is a repeated measures design, everything in our denominator is going to be this error term, right? In fact, here's the table down here that we'll fill out, but note here's where we have error, right? It's part of that variability that's within groups, right? This is the variability that's just strictly by chance. Because remember, the whole point of this sort of ANOVA is to get rid of this between subjects variability, right? We're gonna take this within groups variability and split out the between subjects variability and the error variability. And this is what we're going to use for our denominator, right? So first, let's figure out the between groups degrees of freedom, right? So dfbg, right? That is just nothing more than number of cells, right? Here, I should have all of this in the slides. I don't know if I have the degrees of freedom in here. I probably don't. That's all right. It's number of cells, right? Degrees of freedom for between groups is number of cells minus 1. And how many, or number of levels. So how many levels do we have? 1, 2, 3 levels. So our degrees of freedom for between groups is 3 minus 1. That equals 2, right? So how do we find the degrees of freedom for our error term? It's going to be the number of participants in our our study, right? You know, there was a number of scores. Really, I guess one way to look at it is the number of scores in each level. But of course, that's going to correspond to the number of participants in the study, -1, right? So it looks like we have 5 plants, right? So 5 minus 4. Oops, I don't want to do that. So df between subjects would be 5 minus 1. That equals 4. And then we can find our degrees of freedom. Let's get that right. Degrees of freedom for within groups, which is big N minus K. Right, so we got 15 scores, 3 levels, right? So that's 12. So our degrees of freedom for error, right, is going to be 12 minus 4, right? So that's going to be 8. So now that we're armed with that information, we can look up in our table what our critical value is here, right? And I've got our tables over here. So for the numerator term, we're going to find that value in the row. That's a 2. And for the denominator term, we're going to find that value in the column. That's an 8. So our critical value here is 4.46. So our F critical equals 4.46. All right, and so you haven't even had to do any sort of real math here. The next step is to fill in the table, and you fill in the table by doing all the mathematics that are associated with the test. But while we're here, let's just fill in some of the stuff that we've got. So we'll put a 2 in there. We know our within groups is 4. Our between subjects is, or within groups is 12 rather. Our between subjects is 4. Our error term is 8, and our total is 15 minus 1. That's 14. Right? Okay. So we've got everything that we need in there. So let's just go ahead and cut to the part where we do the math. And what I'm going to do is I'm just going to copy and paste these scores into an Excel sheet. Just put them there. Oops. Let's do that. All right. So I need a few things to get started. I need a T, right? I also need P, and I need sigma x squared. So let's first go ahead and sum up each column, right? This is first year, second year, third year. Now you can do that quite easily in Excel by hitting the sum function. You want to be careful to make sure that it highlights all the correct values, but you can just do that and hit enter. You can do it again for the next column, and then finally for the next column. And you can do the same thing for our participant scores, right? If you line it up just so, or if you line up your cell just so, if you hit the sum function, the sigma function, it'll keep just adding them up. And you can just do this all the way down the line. And let's see, let me just make sure. Yeah. 2, 3, 4. Ooh, why did it do that? Oh, yes, I know. Let's try this again. Yeah, see how I made a mistake there? Let's go ahead and delete that. All right, good. So let me just double check to make sure. Yeah, cells B and D, B through D2, good. B through D3, 4, 5, 6. Okay, good. And now if I go down this corner, if I hit sum, it's going to add up all of these values, which is going to give me the G value, right? So that's G right there. And now let's go ahead and do our sigma x squared values. And if you're doing this in Excel, you can you have space to do this. I'm just going to go. No, I'm going to start with the first column. I'm going to go 9 squared. And now you can just drag it all the way down. Be careful if you're using Excel. You don't want to get a squared value of your T scores. You just want to get a squared value of each of your 5 scores in that particular year. And again, it's so convenient, right? Now that's all highlighted, you can just hit Control C, right? If you go right next to your first value and select Control V for paste, all these values, right? So note here, like I got a 16, so 4 squared is 16, 5 squared is 25, 5 squared is 25. You can do the same thing for the third column as well. And now if I want to get my sigma x squared, I can just run a sum function again. I can highlight that first column, and then I can just again copy and paste my way through. All right, so and then we've already sort of done our degrees of freedom and all that other stuff, but again, n equals 15, little n equals 5, and our number of cells equals 3. All right, fantastic. So now let's go ahead and first do the sum of squares for, well, let's go ahead and do the sum of squares for between groups, right? And so this one, what we're going to do is take for each one of our years, right, for each one of our levels, we're going to take the t value, square it, right, and divide it by little n, right? We're going to do that for each one of these levels, and then from that we're going to subtract g squared divided by big N, right? And so here's how I would do it if you're showing your work, and I think this is a good idea, although you don't even really necessarily have to do all this in the homework, because again, you've already been given, for example, all the sums of squares. But just sort of for future reference, if you were showing your work, I would just break the problem up into sort of constituent clauses, right? So if I'm doing I'll just say this is going to be sum of squares for between groups, right? And I'll give myself a little space over here to do the problem. So right now, and let's go back to the slides. So the sum of squares for between groups, right, is sigma t squared divided by n. So we're going to do all this first, then we're going to do that part, and then we'll finish the problem. So let me show you what I mean. So first, let's go ahead and do the t squared divided by n. Oops, come on. Oh, I didn't put an equal sign there. You got to put an equal sign in front when you're using Excel. All right, so t squared divided by n, which is 5, right? Plus, in fact, sorry, let me go back. Let me use the actual values. It might make it easier for you to follow along. So I'm going to go 51 squared divided by my little n of 5, right? Plus 24 squared divided by my little n of 5, plus 30 squared divided by the little n of 5, right? Okay, and that gives me 815.4, right? And so, you know, I've done this part, right? Now I need to do this part, and then I can subtract these two values. So now I need to do g squared divided by n. So I'll just do it right next to it. So I'll go 105 squared divided by big N, right? Big N, which is 15. Now if I subtract these two values, if I go 815.4 minus 735, that's going to give me my sum of squares for between groups. So what I would do is, if you sort of have to show your work here, I would write all of this out and then figure that out. And so you could write this on one line and then put the answer underneath it. Then I would write this part out. That's right, I want to do this with the actual numbers. It's such a force of habit when I use Excel to just link right to the cells, but oops. It's 105 squared. There we go. Then I would write this out and then put the answer underneath it. And then for sum of squares between groups, what we're going to do is go 815.4 minus 735, and that's going to give us a sum of squares between groups of 80.4. All right. Now let's go ahead and do our sum of squares within groups. And let's go back to our slides here, right? So now what it's asking us to do is figure out the sum of squares for each one of our levels. And again, I'm sort of reiterating that on the homework, I've already done that step for you, but it doesn't matter. I'm going to show you how to do it again anyway, because all of this is a good practice. All right, so to do the sum of squares, again, I would break each thing up so you can show your work. So I'll again move over to this side. So how do we do the sum of squares? Well, we're going to take the sigma x squared, right, for each level, right, minus t squared. I keep, again, such a forced habit of doing this. I'm going to go 527, right, because that's the sigma x squared for this first level, minus 51 squared divided by, boy, I sure have some serious muscle memory to do that. 51 squared divided by 5 plus 118 minus 24 squared divided by 5 plus 184 minus 30 squared divided by 5. Now, it's probably going to give me an error here. So what do I want to do? I want to make sure, oh, I need another parenthesis over here. All right, there we go, 13.6, right? And so that's it. That's all I have to do, right? I don't have to do, what I've managed to do this all in one shot, right? This is the sum of squares for the first level. This is the sum of squares for the second. This is the sum of squares for the third, right? So I can just put that answer right over here. Great. And now if I want to figure out the sum of squares total, I can just add these, and I'll go ahead and use my function to do that. Great, 94. Okay. So now I need to break out this within group variability, right? I need to do something about this within group variance. And so I need to figure out my sum of squares between subjects, and I need to figure out my sum of squares error. So let's go ahead and do the sum of squares between subjects first. And let's go back to our slides, right? So we can remember how to do this. So we're going to use sigma p squared divided by k minus g squared divided by big N. So let's do this clause first, right? We're going to square each p value and divide it by the number of levels, right? So again, we can sort of do this in sort of two steps here. In fact, we've already done, as you can see right here, this is already g squared divided by n. So we've got some of our work done for us already. So what we're going to do is square each p value. So first I'll start with 18 squared, and I'm going to divide it by the number of levels, which is 3. And then I'm going to add that to the next one, right, which is 22 squared divided by my number of levels, plus 24 squared divided by 3, plus 23 squared divided by 3, and then finally plus 18 squared divided by 3. And that gives you 745.66 and some change, right? So again, go back to the slides. What we've done is this part right here. Now we're going to subtract g squared divided by n from that. And again, we've already done that right here, right, as you can see. So what we'll do is go 745.6667 minus 735. And that gives us 10.667. Good. All right. Sum of squares error now. Let's go back to our slides. How do we figure this out? Well, sum of squares error is you're going to take sum of squares within groups minus sum of squares between subjects. That's going to give you your error term. Oops, I don't want that. So let's go 13.6 minus 10.667 6667. And there we have it, 2.933. All right, now we can start filling out our table because we're just about done. There it is. I'm going to minimize this a little bit so that I can see my Excel sheet. All right, so my between group sums of squares was 80.4. My within group sum of squares was 13.6. Between subjects was, we'll just call it 10.67. And for error, we'll just call it 2.93. And then finally, for total, we get a sum of squares of 94. And so now we just need to find our mean squares for between groups, and we need to find our mean squares for error. So we're just going to take the sum of squares divided by the degrees of freedom. So 80.4 divided by 2. And then to figure out our sum of, or mean squares error, we're going to take our sum of squares error and divide it by our degrees of freedom error. That was 8. Okay, so we're going to go 2.93 divided by 8. All right, so 40, we get a mean squares of 40.2 and a error term of we'll call it 37. And now if we divide our between groups mean squares by our error mean squares, we're going to get our F value. And it's going to be a pretty big value. All right, so let me just do this. Oops. F equals 40.2 divided by 0.37. And we're going to get this crazy F value of 108.64. Got a good feeling we're going to be rejecting the null. All right. There we have it. I just want to check it against what I'd already done before. Yep. Why did I get such a... Yeah, okay, I'm good. Yep. All right. So now we have to make a decision, right? Our critical value is 4.46. Our obtained F statistic is 108.64, right? So I think we're going to go ahead and reject the null here, don't you think? Yep. Reject the null. If applicable, compute post hoc. Oh, we forgot to. If applicable, compute effect size. Wonder if I left that off the homework. All right, so we should have a. Let's go back into our slides. Find out how we compute the effect size again. There it is right there, right? So to compute the eta squared for a repeated measures, we're going to take the sum of squares between groups and then divide that by sum of squares between groups plus sum of squares error. So let's go ahead and do that right now. We'll just call this effect size. And so we'll take the sum of squares between groups, right, which is 80.4, and divide that by the sum of squares between groups, which is 80.4, plus the sum of squares error, which is 2.93. And we get an effect size of 0.96, right? So let's say eta squared equals 0.96. Now, if applicable, compute the post hoc test. Okay, great. So remember what we need to look up our Q value. So our little equation is going to be Q, right? Q times the square root of, let me just find it for you here so you know where to look for the post hoc. Although, again, I don't think this has to do. There it is. Q times the square root of the mean square error divided by little n. All right, so first thing we need to do is look up this Q value, and we'll use the 0.05 section over here. So what's our K? Our K is 3, right? We have 3 levels. And our degrees of freedom for our error term is 8, right? So we're looking for a Q value of 4.04, right? So I'll just keep moving this down. Yeah, I'll just move this, put it over here. Q equals 4.04. We also need our mean square error, right, which is 0.37. And we need our little n, which is 5, right? And so the way we're going to compute this, right? So the way to compute our Tukey's is by taking 4.04, right? And multiplying that, right, by the square root of our mean square error term divided by our little n. It gives us a Tukey's of 1.0, yeah, we'll call it 1.10. So before continuing here, I need to get my means, right? Because I'm going to subtract each one of these possible mean combinations from one another, compare it to this value in the Tukey's, and see indeed whether or not I have a significant difference here. And you can do this pretty easily in Excel, right? So I'll just make a row for means, and you can take advantage of what the average function here, right, by selecting that. And then again, just make sure that you only, you have to be careful here if you're using Excel in conjunction with sort of doing your work by hand. Note that I'm taking just the 5 participant scores. As a matter of fact, if I were you and you were using Excel, I would have a little column here, a little header. 1, 2, 3, 4, 5 to help you keep track of it. Anyway, you can, and then you can just copy and paste this, right? So, I can copy this here. It's nice because since you're just doing this in sort of neighboring sort of cells, well, you guys have used Excel before. You understand what I just did. All right, so now what I'm going to do is, well, geez, I don't even need to do the math here, do I? Right? Like every single one of these possible combinations is going to be greater than 1.1, right? Like 10.2 minus 4.8 is definitely going to be greater than 1.1. 6, I think 6 minus 4.8 should be greater than 1.1. Let's just double check. Yeah, 1.2, just barely, right? So each one of these means is significantly different than one another, right? So this is pretty easy, right? So looks like 2016 was the hoppiest year, followed by 2018, and then 2017 was the least hoppiest year. But yeah, all of these means are different. While we're here, since we're going to write up our results in APA, let's go ahead and get these standard deviations. And again, Excel has a function for that too. All right, so let me pull this back up though. So it says, if applicable, compute the effect size, right? We've done that already. And remember, you would want to put in here, you'd want to show your work a bit, so you'd want to say 80.4 divided by 80.4 plus 2.93, right? And when you're asked to compute the post hoc test, again, you could show a little bit of your work here as well, right? So what did we figure out for the, let me just move this one over here, I guess. Here we go. So, right, we got a Q of 4.04 times the square root of 0.37 divided by 5. And that equaled 1.098, and let's just call it 1.1. And then, to be clear, you're probably going to, I mean, this is pretty trivial, but you want a 10.2 minus 4.8, and that's going to give you a value. And then you're going to go 10.2 minus 6, and that's going to give you a value. And then the last combination is 4.8 minus 6, and that's going to give you a value. But the point is that all of them in this case are going to be greater than this 1.1 that we figured out for Tukey's. All right, so now we can write up our results. All right, so we reject the null. The one-way repeated measures ANOVA revealed, oops, can't spell, you guys know that. I spelled it so bad it won't even give me the option. Revealed a significant difference in hoppiness between years. Is that not a word? It should be a word. Hoppiness. No, not happiness, not hippiness. Hippiness is a word, but hoppiness isn't. Okay, fine. So now we're going to report our F, right? And our degrees of freedom going to be our between groups term and our error term, right? What was our ridiculous ANOVA that we came up with? 108.65. So 108.65. P certainly less than 0.05. And let me get our eta square. Equals, what did we figure that effect size was? 0.96. Okay, and remember that if you're typing this out, you want to italicize the P and you want to italicize the F. That's the APA way of doing things. Okay, and now let's just show how our comparisons of means worked. Post hoc analysis revealed that 2018, 2018 hops. How do I want to say this? Hops were hoppier? Oh, bitter, that's it. Right. The 2018 hops were more bitter than both 2017 and, I know it's the 2016 hops. 2016 hops were more bitter than both 2017 and 2018 hops. 2018 hops were also significantly more bitter than 2017 hops. Okay, and now I can insert my means and standard deviation. So 2016 hops, so we'll go mean equals 10.2, standard deviation equals, we'll say 1.3. And remember, italicize any English letters. And I'm going to make life easy on you. I'm going to copy this, just change the values. So after 2017, I'm going to report the 2017 values, which was a mean of 6, and a standard deviation of 1. And I'll call it 1.0 to make it look nice. And then 2018 hops. Pay attention. Actually, this is 2017. This is the 2017 data right here. Right, so I actually want to change that to 4.8. And I'll just change this to we'll round it to just 0.8. That's fine. And then 2018 hops, that's the one that was 6 with a standard deviation of 1. Remember what I said in class, it's tough to keep all this stuff straight, but that's the key, is just sort of making sure you're organized here. So let me just give it a read through and make sure that it makes sense, right? So we reject the null. The one-way repeated measures ANOVA revealed a significant difference in bitterness between years. Okay, so I report the F statistic. All of that is correct. Post hoc analysis revealed that 2016 hops were more bitter than both 2017 and 2018 hops. 2018 hops were also significantly more bitter than 2018 hops. All right, that's good enough. That's fine. That'd get 100%. Okay, so boy, these sure do take a long time to do. But all right, so that's it. Let me know if you have any questions.